With all the code we've written so far across different courses, we've iterated over quite a few arrays using for loops. Broadly speaking, there are two primary reasons you iterate over a collection using a loop. One, to use the elements in the array for some computation. Let's say you have an array of names, and for every name in the array, you want to use it to print out a string of some sort. The second case is when you want to transform the elements in the array. Let's say you have an array of numbers, like we just did, and you want to double each value in the array. You could do it like this. Now, I have a new playground page here for the new set of videos. And in here, I'm going to declare an array called values, again with 1, 2, 3, 4, and 5. Now, remember, again, we want to end up with each of these values doubled in a new array. So I can create a new array. And for the type, we'll set it to be an array of integers. And then I can use a for loop, iterate through the array, through the collection, and I'll say new array dot append number times 2. So this here, what we just did, is called an imperative approach. What do I mean by imperative? Well, with imperative programming, you tell the compiler what you want to execute line by line for each step. The alternative to this is known as the declarative approach. In declarative programming, you write code that describes the end result. You don't write the intermediate steps for how you want to get there. The code we just wrote, applying a transformation to each member in the array, is exactly what the map function does. The difference between the two is that map is a declarative approach. So take the following example. You can say let doubled numbers equal values.map $0 times 2. So in this line of code, all I'm saying is that I want to iterate over the array and multiply each value by 2 and get a new array back. So this is the declarative style. I'm not saying that I want to use a for loop and then iterate over each one. With each one, I want to take that and multiply it by 2. That's abstracted away. Using this approach, the two main differences that are glaringly obvious is that in the imperative approach, my final array, new array, is mutable. It's declared using var. And remember, we don't like mutability. It can lead to unexpected results. The declarative approach, on the other hand, results in an immutable value, as you can see here. This value is directly assigned, this new array is directly assigned to a constant. You may have often heard of functional programming. Functional programming is a declarative style of programming where we use many small functions that return immutable data types. We abstract away the code that indicates how we want to do things, but instead say what we want to do. Wherever you see the map function, it should be immediately clear that this means one thing. You are applying a transformation function to an array of values and getting an immutable new array back that does not mutate the original dataset. So that's the second major difference. Here, we're not mutating any array. So what does this have to do with closures? Well, as you can see, the map function takes a transformation function in the form of a closure expression that it then applies to each element. Along with map, there are few other functions in Swift that allow you to program in a more declarative style with less mutation. To truly understand how they work, though, rather than just showing you how to use them, let's build each function from the ground up. In doing this, you'll also gain a much better understanding of how closures are used across our code. So the first function we're going to build is the map function. We're going to declare the map function as part of the array type, so let's do this in an extension. So we'll say extension array. When we built the apply operation function earlier, we had a parameter that was essentially the transformation function, except that it was hard-coded to accept only integer values. The map function doesn't work that way. Instead, the signature of the transformation function that we pass in, the closure expression, depends on the array that you call map on. Remember earlier we said that map knows that an integer is being passed in here because values is an array of integers. So the signature of this function that is inferred depends on the collection that we're calling map on. If you call map on an array of strings, for example, it expects that the transformation function takes a string as an argument. What about the return type? Well, the return type depends on what you actually do in the transformation function. For example, here we're just multiplying an integer by an integer, so the signature returns an integer. If your transformation function returns a Boolean value, that's what the return type of the map function is. So how do we take all this into account when defining our own version of map? Well, we use generic code. Earlier, you learned how you can create generic types and functions that work with a range of different types. Map is no different. So let's create this new version of map. We'll name ours custom map so as not to conflict with the built-in one. Now, the map function is generic over a type t. It takes as an argument a transformation function. So transform, and the signature, the type of this function is element to t. We know that the array type itself is a generic type, and so element here refers to the type parameter defined in array. T is the return type of the transformation function. If we pass in a transformation function that takes an integer value from an array of ints and returns a string, well, t will then be a string. But remember, the map function returns a new array, so the return type of the custom map function is an array of t. Inside the body of the map function is the code that we're used to. So first, we're going to create an empty array of the same type as our return type. So we'll say var result equal to an array of t. Next, we're going to iterate over the elements in the array and apply this transformation function to each value. So for x in self, we can say result, which is the array we just created, dot append, and then we'll apply the transformation function, which takes as an argument an element instance, which here is represented by x. So we'll say x, and the function guarantees that it'll return t, so we can go ahead and append that to result, which is an array of t. Once we've done that, we can return result. Remember, the goal of a declarative approach to programming is to abstract away the how. Here, our map function, custom map, is taking care of the iterating over the array and applying the transformation function to each value. This is the how. Our goal in using custom map is to provide the what, the transformation function, what we want to do to each element. So let's see how we can use this. For example, we can say let integer values, and I'm just going to create a new array on the fly, an array literal. So I'll say 1, 2. Now these are string literals representing numbers, okay, up to 5. And we're going to call custom map on this. Now we need to provide a closure expression here. Remember, because this is first the only expression or the only argument to our function, and the last argument, we can get rid of the parentheses and just provide a trailing closure. And here we'll say int $0. So in this example, I'm iterating over an array of strings, this one right here. The transformation function accepts a string because element is of type string here, and then it tries to convert that to an integer because this is the initializer for the int type and $0 represents that first argument. Now, this int function, this integer initializer, has a failable in it. Basically, if the string can be converted to an integer, we'll get an integer back, but if not, we'll get nil back. So the return type of this function is optional int. That means if you look here, since this is an optional int, the return type of custom map will be an array of optional ints. And if you check the type here, you'll see that it is an array of optional integers. Since the map function, both the real map and custom map, are generic, the return type of the function is determined by the return type of the transformation. Let's look at one more example. So I'm going to copy-paste some helper code in here. So here I've just created a tiny struct with a static method that accepts a string containing a date in a particular format and returns an optional instance of date. Date is the foundation class to work with date objects. If we can convert the string to a date, we get an instance of date, otherwise we get nil. Next up, let's define an array of date strings. So we'll say let date strings, and to that, We'll assign a few strings containing dates. So I'll say 20th October, 1978. 11 January, 1947. And finally, 28 March 2002. Using our custom map function, we can map over this array and transform each string value to an instance of date. And this is really simple. We'll say let dates equal dateStrings dot custom map. And inside the transformation function, we're going to use the formatter object I created that has a static method, date from string. And remember, each argument passed in is represented by $0. And that is it. So you'll see that, what does this say here? Oh, hold on, let me inspect dates. There we go, that works. And now if I say print dates at the bottom, you'll see that each of those strings has been converted to an actual date value that the computer can read. Map is a super useful function that combines the power of generics and closures to allow us to transform arrays. You may be thinking, wow, now that I know how to use map, why should I ever use a for loop? These are really two distinct tools and can't be used interchangeably. You only use map, in theory, when you want to transform an array by applying a transformation function to go from one type to another. So here we're going from strings to date types. Here we're going from strings to integers. And then up here, integers to integers, but we're transforming it in some way. For loops, on the other hand, are used when you want to perform side effects. What does this mean? If the code you want to execute on looping over the array mutates an object or modifies the state of your program elsewhere in your code, then a for loop is the tool that you need. In fact, if you use map without actually returning what map does and assigning that to a new constant, Xcode will warn you and say that your result is unused, because really you only want to use map to transform some dataset into another dataset. Okay, enough about map. On to the next thing.